All right, so now we're getting into 6.2, where we're going to talk about angles in the coordinate plane. Now, up till now, you've probably dealt with angles in degrees, and we're going to introduce a new way of measuring angles. This is going to be the radian. You've probably seen it on a calculator as RAD, and what it is it's a measurement of the angle that is based off of the radius of the angle itself. So it's actually measured by the circle. It's actually measured by a measurement of the circle, not something that's made up. The degrees are just something that's made up, that we split a circle into 360 parts. There's various different reasons why that was used. One of the most common reasons you may hear is the fact that it was made to back when they thought there were 360 days in a year, or it took 360 days for the Earth to travel all the way around the sun. So essentially a degree was at that point believed to be how far around the sun the thing would go in one day. That's what degree meant. Now, when we talk about an angle in radians, it represents the number of radii lengths that fit on the arc of the circle intercepted by the angle. Now what that means is this: if we have an angle right here that is 1 radian, it means that the length, let me change colors here so it jumps out a little more. The length here of the radius is equal to the length of the arc if we were to cut it off the circle and stretch it out and measure it on a ruler. This length would be the exact same length as that would be if this angle was exactly 1 radian. So that's where the radian measure comes from. And so we know that the arc length, if the radius is 1, is exactly the same as the radius. Sorry, let me back up again. The arc length in radians is going to be exactly what the angle is. That's how they relate. Now, if the radius is 2, then the arc length is going to be 2 times whatever that radius is, or that angle is in radians. So the arc length is going to be the green part right here. Your standard position for a radian measurement in the circle is going to be based off of the positive x-axis. Now this is with the coordinate plane, and this one doesn't exactly pass through the center, but imagine that it does. Whereas we're centering the circle on the origin of the coordinate plane. So standard position is where the circle is centered at the origin, and the initial side of the angle, remember an angle is 2 rays that have a common beginning point. That means that the initial ray is going to be along the positive x-axis, and you're going to have a terminal ray somewhere else on the circle, sharing that common point at the origin. Now, your theta measure is just going to be the arc length divided by r radians. So if you know what the arc length is, you can divide by the radius, and that's going to be your angle in radians. Angles are measured counterclockwise. Now, what that means is positive measure, or measured positively, counterclockwise from the positive x-axis. Negative angles are measured counterclockwise. So if we go this direction, we're getting a positive angle. If we're going this direction, we're getting a negative angle. Now, when we look at the unit circle, or the angle measures, we're not even really on the unit circle yet. This is for any angle, or for any circle of radius, whatever. The angles are as we see here. Notice that all the orange ones are multiples of each other. That simply means that when we go from pi over 6 to 2 pi over 6, which reduces to pi over 3, those are multiples of each other. And we can count all the way around. 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, all the way around to 12 pi over 6. Now you're going to notice that all the way around, angle measure in radians is 2 pi. So that is what we've got there. Now, when we talk about the other ones, the pi over 4s, they are going to add around the exact same way. Now, you're going to notice that they are the same in some places. They hit some places with both the pi over 6s and the pi over 4s. So we've got pi over 4, 2 pi over 4, 3 pi over 4, 5 pi over 4, 6 pi over 4 is right here, 7 pi over 4 is right here, and then we've got 8 pi over 4 right here. You're going to notice that that is going to also reduce to 2 pi. You're going to notice the same thing for all these. 2 pi over 4 reduces to the same thing that 3 pi over 6 does. 6 pi over 6 is going to reduce to the exact same thing as 4 pi over 4, which is going to be pi. And then as you go on around, you see the same thing at all those corners, these main areas here, where the circle hits the coordinate axes. These are called quadrantal angles. They are called quadrantal angles, and that's at where the unit circle is hitting the axes, the X, the Y, positive and negative. Those are quadrantal angles, and that's where you're going to have overlap of the pi over 6s and the pi over 4s and even the pi over 2s, because pi over 2 plus pi over 2 gives you 2 pi over 2, plus pi over 2 gives you 3 pi over 2, and plus pi over 2 gives you 4 pi over 2, which is once again 2 pi. So these are all the angles, and you need to understand what they are. Now, all the pi over 6s, if I tell you that pi over 6 is equal to 30 degrees, what does 2 pi over 6 equal? Well, if 1 pi over 6 is 30, 2 pi over 6 is 60. And what is 3 pi over 6? Well, 3 pi over 6 is 3 times 30, which is going to give you 90. And you can work the same way all the way around. And we'll look at these in class on a big, huge unit circle that we'll fill out. All right, so an angle in standard position has a measure of 2.7 radians. In which quadrant is the terminal ray of the angle? All right, so we know it's in standard position, so we're starting off at the positive x-axis, and it's a positive angle, so we're going to go counterclockwise, and we want to go 2.7 radians. Well, here's the thing. We've got to figure out where 2.7 falls. Let's go back real quick. Back. There we go. And we're going to look at it. Remember, our quadrants are still this exact same that we've learned them before. This is quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. Now, you need to always, always, always remember that pi is equal to 3.14. Let me write that correctly. 3.1415926, and it keeps going forever. We're going to focus on these numbers right here. So 0 and 2 pi, so if it's the starting position at 0, if we've gone all the way around, it's 2 pi. So from 0 to pi over 2 is going to be quadrant 1. Well, what is pi over 2 when we talk about something that doesn't have the pi in there? Well, take that number right there, just divide it by 2. So pi over 2 is going to be roughly 1.57. And then pi, of course, we know what it is. It's 3.14. And then 3 pi over 2, that means we're just going to take 3.14 and we're going to take 2 pi over 2 and add pi over 2 to it. So we're going to add 3.14 plus 1.57. So 3 pi over 2 is going to equal 4.61. Nope, 7.1. I counted wrong. So 4.71, and these are numbers you should kind of stick in your head because you're not always going to have that pi in there. But just remember, if you need to find that, you know what pi is, so you can find out 3 times 3.14159, or 3.14, divided by 2, gives you 4.71. Then back over here to 2 pi, gives you 6.28. All right, so now back to our question that we were asked. We're looking for a measure, make this a little bigger here, of 2.7. No pi, 2.7 radians. So where is 2.7 going to fall? Is it going to fall between 0 and 1.57? Or is it going to fall between 1.57 and 3.14? Or is it going to fall between 3.14 and 4.71? Or 4.71 and 6.28? Well, of course, hopefully you know it's going to fall between 1.57 and 3.14. So somewhere in here, we're going to have a measurement of 2.7 radians. So it's going to fall in quadrant 2. All right, so the radius of a circle is 8 inches. And a central angle of the circle has an arc length of 26 inches. And by the way, S is it's what we use to represent the arc length. Not really sure why, but it is. All right, and that's 26 inches. So what is the measure of the central angle in radians? Well, remember, we saw that equation where theta is equal to the arc length divided by the radius. So in this case, it's going to be S divided by R, or 26 inches divided by 8 inches. And that's going to give us 3.25 radians. Now, this is a good time to bring this up. What do you notice happens right here to our units? If we divide inches by inches, they're going to cancel out. So magically in here, somewhere we get radians. Where does it come from? Well, that's the thing. Radians is more a description of what you've measured than it is actual units. Because remember, we're talking literally the length of this divided by the length of that. It doesn't have a unit. It is a proportion. So radians is not really a unit. So when you get further on in math, especially in calculus, you'll see some situations where you throw a radian in there, then all of a sudden, boom, you've got an answer. And if you put radians in, it gives you some crazy contraption of radians per inches, or radians per radians times inches squared, or something like that. So understand, radians are not technically a unit. It's just a way to identify what ratio you're giving. You're giving the ratio of the arc length divided by the radius. I know that's confusing, but just trust me. Radians can kind of be there, it can kind of not. And by the way, if you write an angle, if you write 45, and you do from here on out now, if you do not put the degree, let's say you forgot the degrees, it is understood that you just said 45 radians. Those are very, very, very different angles. So if you're talking degrees, you must put the degree symbol there. You can get by with not putting radians, but you cannot get by with not putting degrees. All right, number 3, an angle in standard position has a measure of 4 pi over 3 radians. Find 3 coterminal angles. Now, coterminal let's go ahead and get an equation, not an equation, but a definition here. Coterminal angles are angles in standard position. Once again, centered at the origin. The initial side is along the positive x-axis and the terminal side is elsewhere. Angles in standard position that share terminal sides. Other angles. All right, so let me see if I can deal with the circle here. All right, let me get this a little smaller. So we'll say that's the positive x-axis. So we're measuring from here. And let's say we've got an angle. We're going to go here with our initial side. And let's say we've got a terminal side over here. Actually, let's go ahead and do that one where it needs to be. 4 pi over 3, that's going to be greater than pi. It's going to be 1, it's going to be pi over 3 greater than pi. So straight over here would be pi, and it's added pi over 3 to it. So this right here is 4 pi over 3. Now, if I want to have the exact same initial side and the exact same terminal side, there's a couple of ways we can do that. We can do it where we go around this direction, but we keep going and we come back around over to the other side. And what did we do? Well, we went to there, but then we went an entire circle back around. Well, what's an entire circle in radians? 2 pi. So we could have 4 pi over 3 plus 2 pi, and that would give us a coterminal angle. Now, if you go and you add this and you get 4 pi over 3 plus 6 pi equals 6 pi over 3, I'm going to punch you in the soul. Remember, you've got to have common denominators to add these. These are still fractions. 4 pi is just a number. 2 pi is just a number. Those have to be common denominators before you can put them together. So we end up rewriting the 2 pi, multiply top and bottom by 3, and you end up with 6 pi over 3. Still equal to 2 pi, check and see. So then we're going to get 10 pi over 3. There's a coterminal angle. Well, guess what? If we can add one circle, what's going to keep us from going ahead and doing 1, 2, and 3? We can do that again. So we could take our 10 pi over 3 and we could add our 2 pi again in the form of 6 pi over 3. Since we've already got a common denominator, we shouldn't have to do it again. And then we can just go ahead and add that, and you're going to get 16 pi over 3. Notice those are not reducible, so that's good. If it'll reduce, reduce it. If it doesn't, don't. Now, there's one other way that we could do it. We could do that forever, by the way. We could continue to add 2 pi and 2 pi and 2 pi and 2 pi and have an infinite number of coterminal angles. But what about another way? Let's look at another direction. Well, if we start here and we go backwards, let me make this line bigger so it's a little easier to pick out from all that other stuff. And we go backwards this way, we can find out what that angle is, and that's a coterminal angle too. It still has that initial value, that initial side, and it still has that same terminal side. We just got to find out how far we go this direction. Now, how in the crap do you do that? Well, here's the thing. We know if we go from here all the way around, it's 2 pi. But we don't want to go all the way back around. We only want to go this far around. So we want to go this far around, and we want to not go that much. So we're going to subtract the 4 pi over 3. So we're not going all the way around. We're going to subtract the 4 pi over 3 and get it there. Now, this is not the only way, and I'll show you the other way to find this in just a second. So, of course, we need a common denominator again, so we're going to do 6 pi over 3, 6 pi over 3, and we end up with 6 pi over 3 minus 4 pi over 3 gives me 2 pi over 3. All right, so the other way is kin to this one right here. If we can add 2 pi and add 2 pi and add 2 pi and get coterminal angles, guess what we can also do? We can take it from 4 pi over 3 and subtract 2 pi, subtract 2 pi, subtract 2 pi. So in the same way we did this, we could do 4 pi over 3 and subtract 6 pi over 3. Remember, that's 2 pi. And we still get negative 2 pi over 3. That's actually probably the better way, because what did I make a mistake on right here? I found this angle, but I neglected to put the negative in front of it, where this one, automatically the negative is going to be there. Whichever way makes more sense. Now that I've done both of them, I kind of like this one better. All right, so number four, we've got to do a little bit of thinking here. It says the 12 points shown are all equally spaced around the circle. Angle 1 in standard position has a terminal ray that passes through point A. We've got to find where point A is. If measure of angle 1 is 7 pi over 6, label point A. And then we've got to label point B with this information. But let's go back over here and think. All right, so 12 points. So we've got 2 pi is the whole circle. That's all the way around. If we're equally dividing that into 12 parts, what does each part do? Well, each part sweeps out pi over 6. So if each dot sweeps out pi over 6, there's pi over 6, there's 2 pi over 6, there's 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, and that is A. So there is point A, and there is your angle of 7 pi over 6. All right, angle 2 is in standard position and has a terminal ray that passes through point B. If the measure of angle 2 equals negative 5 pi over 3, label point B. Now, here's the thing. Since we know our dots are counting off in sixes, why don't we take this and make it into sixths, pi over 6s instead of pi over 3s. So negative 5 pi over 3, multiply by 2 over 2, Why can we multiply by 2 over 2? Because that's a big fat 1. It's not going to change the value of this thing. It's just going to change what it looks like. So we end up with 10 pi over 6. So now if we're doing negative, we're going to go backwards. We're going to go clockwise. So 1/6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, and 10 pi over 6. So right there is B. Right there is B, and the angle we're measured is right there, and that is negative 10 pi, whoop, I can't write, negative 10 pi over 6, which is negative 5 pi over 3. All right, that's all of section 2.